Okay, so let us continue. So basically, last time, right, we went over the list of the random variables, right? Namely the hypergeometric, the geometric, the negative binomial, and the Poisson, right? And we talk about their expectations, variance, right? Mass function, and what they model, right? And their connections. And so the problems, right, we discussed so far. So here, right, this problem is related, right, to the binomial distribution. However, right, to access that binomial distribution, you need to go through the cases, right, which basically will be controlled or expressed by the law of total probability, right? And so once you decide what case it is, then you can use the binomial, right, distribution appropriate, right, for that case. Similarly, right, here is a similar situation where, right, you also have the binomial, but the binomial, right, also depends on the case, right? The cases, whether the person's guilty or not. And so again, right, we need to use the law of total probability to access, right, the cases. And then from there, right, we can decide, right, how to compute the binomial distribution, right, according to the situation. But notice, right, here, the logic is slightly different, right? I guess the events that the binomial should follow are not quite the same, right, as the previous ones. Because, right, I guess the language of the legal, right, is different from the language of the satellite functioning. Okay. And so that was part A, right? This is the answer to part A. Now let's take a look at part B, right? How do we do part B here? So even though, right, the question is about what percentage, it really, right, is still about basically, so let us get that into a fresh. Right, even though it says what percentage, right, is really about probability, right? So the probability of a person, right, being convicted, right, that's going to give you the percentage anyway, right? So what should we do here to find this probability?
Professor, do we still know that 65% of the defendants are guilty?
Yeah, I think the data, right, applies everywhere the same.
Oh,
It's the same. It should kind of put this on top, but yeah, it's the same data. Absolutely. All right, so that's actually on point, right? Basically, we need to break it down into cases, right? And so the law of total probability is still, right, the point of part B, right? And so 65, and then, sorry, plus, right, 0.35, right? Now, what do we know if a person is guilty? Votes a guilty person, innocent is 0.2, right? So if we let X be the vote of conviction, right? Then X is binomial 12.8, right? Also guilty person innocent would probably 0.2, so vote a guilty person guilty, right? Probably 0.8, right? If guilty, right? And that'll be binomial 0.1, right? If not guilty, right? So let me say this is number of guilty votes, right? Say it that way, right? Okay. And so therefore, if you're guilty, right, you need at least 9 votes. So that's 9 to 12. K, right? 12 choose K, 0.8, 0.2, right? And then 9 to 12, 0.1, 0.9. Right. Any question about this? Okay. So let's take a look at part 3 here. We're switching, right? I guess the title says it all, but at least try to see, right, why we're dealing with a Poisson distribution here and what exactly is Poisson. Okay. So what kind of random variable do we want to track here?
The number of errors in the article?
Right. Number of typos, right? In article. All right. And what distribution does X have? So the question is probably X equal to 0, right? But what distribution does X have? So we're only given the average, right? And of course, here, right, the context and the fact that only the average is given, right, tells you that, right, this is one of those Poisson approximation case. So X will be Poisson three, right? If you use a first typist. And it will be Poisson 4.2 if it's second typist, right? And so how do we handle probability X equal to 0 using this information? So actually here, right, we still have to take care of the law of total probability. Right. And it's equally likely, so it's a half each, right? What is the first probability? So it is a Poisson 3, right? So we can say And then this Poisson 4.2, right? Now what is this? And what is this? So if we take a look, right, the Poisson distribution has this probability, right? So probability x equals to 0 is e to minus lambda, lambda to the 0 over 0 factorial, right? Which is what?
It would just be the e to the minus lambda.
Correct, right? Because 0 factorial, right, is equal to 1. So the answer here will be e to the minus 3 and then e to the minus 4.2. All right, any question about this? All right, let's take a look at this one. All right, so here, right, this problem has 4 parts, and you'll see that each part we may track different random variables, right? So we need to spell it out carefully for each. So part A, right, the random variable we want to track, right, should be the number of people hit by lightning, right, in a month. Okay. And the question, right, of course, asks for probability x bigger than or equal to 8. What distribution does x have? So based on the kind of something like problem 3, right? We could guess that X is a Poisson. But if with a Poisson, then we need to give the lambda, right, parameter. What is lambda in this case? So we see, right, that the rate is 1 per 100,000. Well, we have 400,000, right? So that would be 400,000, right? Times 1 for 100,000, which is 4, right? And here we see that scaling, right, property of the Poisson. If the Poisson, right, if the town population is different, like a million, right, then we can still do the question, but with a different lambda by scaling lambda appropriately. And once we identify X, then probability, right, X equal to 8 will be, so here, right, it should be done by the complement. The reason is simple. If we sum from 8 to infinity, the expression is not incorrect mathematically, it's fine, right? But when we need to implement that expression, then that infinite sum cannot be calculated exactly. And second, right, writing down, right, even trying to compute that sum for 10 terms is inefficient compared to, let's say, 8 terms, right, that we have to calculate for the conjugate, for the complement, right? So just a technicality, but if it's more efficient to do it that way. Any question about this? Okay. So let's take a look at B. What random variable are we tracking in part B?
The months, number of months that
Number of
have 8 or more
months,
people.
right? So if we let y, right, be the random variable, let y be the number of months, right, with 8 or more, right, lightning hit. Okay. Then we want the probability of y equal to 2, right? Okay. Then we want to know the distribution of y, right? What distribution does y have? Is it Poisson? Hypergeometric? Negative binomial? or something else, something we haven't talked about?
Is it the Poisson?
Okay. If it's Poisson, then let's just look at the support, right? A Poisson will have support from 0 to infinity, right? Roughly speaking. Now, if we look at the number of months with 8 or more, right? People hit by lightning. Is there an upper cap here in this question? Is there a cap on how large y can be?
Oh, the cap would be 12.
Right, it says in a year, right? So Poisson would not be the right answer here just from that reason. So what distribution does y have? Well, if we look at each month, 1, 2, up to 12, right? What do we do with each month? A month will be a successful month, right? If we have 8 or more people get hit by lightning, correct? That'll be a successful month. So maybe yes, maybe no, maybe yes, etc. Right? And we count a number of successes, right? In total, in 12 months. So what does that look like? That looks like a binomial, right? With binomial, we have the number of trials and the success probability. And we need to identify both. What's the success probability here?
It would be the answer to A.
Correct, right? Yeah, exactly. E is exactly answering. And so, right, probably y equal to 2. Again, for the same reason, right? It will be the sum from 0 to 1, right? Of 12 choose k, p to the k, 1 minus p to the 12 minus k. Right. Any question for this? All right. What about C? What are we tracking in C? What is it that we're keeping track of to answer the question in part C?
Would it be like easier to do this by using the complement? Um, you'd be tracking like the months consecutively that you would have like less than 8 people hit by lightning.
No, I mean that sounds right. That's true, right? So what when you phrase it like that, that's actually right. Actually, the word consecutive also is actually correct, right? But the reason why we want to kind of slightly modify what you said, right? So what when you say that, you actually are thinking of a slightly different random variable. Let's say number of consecutive, right? And this is important. That word is important. Months, right? Where you have less than 8, right? Hit, right? That actually is a very good description, and that would serve to kind of tackle this question. But notice, right? If you name it like this, it's actually not question. Just to point out to you, then the question is not about z equal to I actually that they're asking. All right, you see why? So that's the first disadvantage. The second disadvantage, again, it's not too bad here. It's just basically, right, it's not within the model that we use. Not that, again, right, it's a big deal. But if we could, we just throw it into, right, the ones that we have dealt with, right, we have knowledge of. Because, for example, here it's about probability, so it's probably easy to write down, actually very trivial. But what if the question is about expectation, right, or variance? Then again, right, identifying with the random variable we have knowledge of, right, will be beneficial to us because then we don't have to do all the computation fresh. All right. So instead of doing this, right, and I'll point out why, you want to define z as a number of months until, right, the first frequency rate hit. Okay. What's the difference between your definition and my definition? The difference actually, let me call this z prime, right, to identify, to distinguish. Mine is yours plus one, right? Because I do count, right, the last month that, right, you got the first, the month that has the first, right, more than 8 hit. Okay. And this distinction exactly is the distinction also that comes up in the definition of the negative binomial. Do you count the number of failures or you count the total number of trials, which is failures plus how many successes you are looking for, right? Again, both definitions are valid, right, to describe the same phenomenon. But I guess one of them have, let's say, better machinery, right? So, and also notice here, right, will be the month. They say that the first month you have, right, number I, right? And also present month is number one. If you define like this, you have to start counting from 0, things like that. So here, right, the probability in question is for z prime equals to I. So that will be p to the I minus 1. Sorry, 1 minus p, right, to the I minus 1 times p. P again, right, is answer A. Right. So that's probably easier that way. So it's a geometric random variable, right? That's what we're getting at. Right? Any question about this? Okay. So, right, there are 500 people, right, tested for some rare disease, right? So notice, right, for example, in part A, right, if we want to have the number of positive, right, test, then precisely, right, if you want to talk about precisely, then what distribution does X have? Precisely, X has a binomial 500, 1/1000 distribution, right? But for the reason we pointed out before, we don't want to deal with this binomial, right? And that's also the word approximation here. So approximately, X will have what kind of distribution? It'll have a Poisson distribution, right? With what kind of parameter? Oh,
500 times 10 10 to the negative third power.
yeah, right. It's binomial 10p, np, so that's that, which is 1/2, right? And so the question asks for probability that at least one person has the disease, right? The probability X bigger than or equal to 1, which is 1 minus probability X equal to 0, right? Which is 1 minus beta minus 1/2, right? Now, let's take a moment, right, and try to see what the big deal is if we use a precise distribution. What happens if we use the binomial to answer this question? If we use the binomial to answer this question, that will be 0.999, right, raised to 500. Correct? And our claim is approximately this, right? Again, okay, because this is an approximation. Now, why do we prefer this and not that? again, right? For example, what is this number to some precision? Well, right, if you plug in a calculator, I think you probably get, actually, I don't know. What is this number? Is it small or big? Or whatever, right? Is it close to one? Notice, right, the error here is huge, right? Because this is close to one. So you raise it to 500 power, probably is a huge error waiting, right? While e to the minus one half, well, right, you could do whatever precision you want, right, etc. Right. So that would actually help to, right, control the approximation much better that way. Okay. Okay. Now, what about part B? What kind of probabilistic statement is part B?
Is it still a binomial? But
No,
oh,
well, we would still go with Poisson, but what kind of probability are we asking about this? The binomial, right, is a precise
oh yeah.
distribution. We're just not going to use it for computational purpose.
I mean, so you would have like uh the answer in A, and then just minus the probability when it's exactly x is exactly one, divided by the answer in A.
Right. So in part B, right, it's really about probably x bigger than one, given x bigger than equal to one, right? So like that, which exactly, right, is the answer in A. So um, well, so it's probably x equal to zero, right, and x equals to one, which is what? Probably x equals to one is one half, right? And then like that, right? So now for part C, the focus is on a particular individual, Jones, right? So what's the difference when we move to Jones here compared to before?
It would be like 499 people and like one person,
Right,
at least one person.
correct. So here, right, because Jones already knows he has a disease, so he counts as one, right? But he's looking for at the rest of the people. So the distribution now, right, is, or if you want, is a different random variable, kind of, right? Y is the number of positive, right, of the remaining 499, right? Something like that. Let me, right. So C, right, Y is exactly the number of positive in, right, remaining 499 people, right? So Y is still approximately a Poisson. But the Poisson now, right, is 499 over 1,000, right? Small, but significant, right? We want to keep that. And so more than one, right? So really, we are looking at Y plus one, right? Is the random variable we're interested in. Because plus one, because Jones has the disease, right? So it's something like probability Y plus one is more than one, right? Which is the same as probability Y equal to one, right? Which is one minus probability Y equal to zero, right? Okay. Any question about this? All right. So now we want to test everyone individually. First, I plus minus one were negative. The ith, right, was positive. So now, given the scenario, given this, right, that basically you have I minus one and then I, what's the probability that the remaining people have the disease? Any of the remaining. So what are we looking at? Right? And so by same logic, we just have to subtract that. And we want any of the remaining people, right? So actually it's probability Z equal to one, right? The only requirement here, of course, is that for the Poisson approximation, right, to work, this has to remain large. So we want I to be kind of small, maybe up to 10, 20, something like that, right? The moment I becomes like 300, 400, the approximation starts to get bad, right? Because the remaining people now we only have about 100 people left. It's probably not big enough, right, of a binomial for the Poisson approximation. Apologize, right? Oh, this is over 1,000. Any question about this? All right. Well, looks like this is the last one, I think. So let's see if we can do part A, and then we'll do the rest after the break. Actually, we could do A and B together if we want, right? So in both A and B, right, what are we tracking here? What's the random variable that we're looking at? In both A and B, right, we're both looking at the number of people who would agree to interview, right, on the list. This is important, okay? As the C and D part be different, right? The random variable we're tracking in part A and B are the number of people who would agree to answer, right, interview on the list. Okay. Right. So let's give you the quiz and then we'll continue with this question. Right? Well, let's have you answer this one, right? Part A. All right. Any question before we take a break here? All right. So we'll continue at 7:05. Is there any question before we continue? All right. So right. So here, right? If we look at A and B, both of these questions, right? We'll try to track the number of people, right, agreeing to interview on the list, right? Now, of course, so what we're saying is it's the same description for both A and B, but because the lists have different size, right, in A and B, so they're not the same random variable, right? So what random variable or what distribution does X follow in A, and what distribution does X follow in B? And what question are we asking? What distribution does X follow in A and B? So we see that, right? There are 5 people on the list, and each person, right, independently agrees to be interviewed with probability 2/3, right? So if we look at each person on the list, 1, 2, 3, 4, 5, right? We see that person number 1 agrees, right, to interview with probability 2/3, and disagree, right, with probability 1/3. Person number 2 independently, right, agrees with probability 2/3, disagree probably 1/3. Person number 3, right, independently agrees with probably 2/3, disagree with probably 1/3. Person number 4, right, independently agrees, probably 2/3. Disagrees, probably 1/3. Person number 5, right, also independently agrees, or 2/3, and disagrees, probably 1/3. So what does that seem like about the total number of people agreeing to be interviewed on this list? Well, looks like we're counting, right, the total number of success, right, in 5 trials, right, that are independent, and each of them have a probability of success 2/3. So that looks like a binomial, right? 5 2/3. Correct? And the interviewer needs to interview 5 people. So therefore, we're looking at probability X has to be at least 5, right? And that, of course, is probability of a binomial 5 2/3 has to be at least 5. Well, this binomial, right, can only be at most 5. So that can only be 5, right? Which turns out to be 2/3 to a 5th. Any question on this? Okay. What will part B? What distribution does X have?
That would be the X is larger or equal to 5 in a binomial distribution of 8 people and 2/3.
Excellent, right? Exactly. And so we look at probability X be going to go to 5, which is a sum, right, from 5 to 8 of 8 choose K, and then 2/3 to K, right, 1/3 to 8 minus K. Right? Very good. All right. So now for C and D though, right? We kind of zoning in for part B, right? So we have the list of 8 people now. But now, right, we are interested in what? The speaker will, sorry, the interviewer, right, will speak to exactly, right, this many people on the list. So C or D, right, the random variable we're looking at is the number of people, right, I guess the interviewer speaks to, right, speaks to do what? To obtain 5 people, right? Correct? That would be the number of people, right, that you will speak to. Exactly. Agree? So having said that, what distribution does Y have in C and D? what distribution does y have in this case?
Is it a negative binomial?
That's correct, right? Exactly. So the point is actually, right, for A and B, the language will give you a binomial because you just look at the people on the list. But C and D, right, is exactly about a negative binomial. And both of them, right, will be a negative binomial. You're looking for 5 successes, right? 2/3. And so for C, that's probably y equals to 6, right? And for D, it would probably y equals to 7, right? Do you remember what that is? So 5 choose 4, right? 1/3 to the 5th, and then 2/3, right? Sorry. When you need 5 successes, right? And this is 6 choose 5, 6 choose 4, right? And then 1/3 squared, 2/3 to the 5th. Correct. Right. So note that in C and D, for example, right, and even A and B, it's possible, right, that when the interviewer goes through the list of 8 people, right, she will still not obtain all 5. That's a possibility, right? The 8 is not a cap in that sense, right? The 8 is just whatever that's there, right? So in fact, right, notice the 8, this number 8 here is irrelevant in terms of C and D, right? That doesn't show up anywhere. She could, right? The negative binomial can go beyond 8. So the reason why, right, it says in part B here, first of all, right, it's just to make it not trivial, because if you have 5 people, things are trivial. And you want 6 and 7, right, to be below 8. That's all there is. Okay. Any question about this? All right. So with that, right, with this, we are done, right, with the discrete distribution, right, chapter, if you will. Next, right, we will now do the same thing, but now for continuous random variables. Okay. And so just like the highlight here, if you will, is that having gone through, right, discrete random variables, you want to pay attention to the contrast, right? And there's similarity too, right? We'll look at the similarity and contrast, okay, of continuous random variables with discrete random variables. And the biggest contrast, right, or the biggest standout is right here, right? The continuous random variable, right, has PDF, right? And the reason, of course, is to remember that probability of a continuous random variable taking on any particular value is equal to 0. So that's why, right, we have to go through the language, right, of the density function to describe continuous random variable. Right, so that's new, right? And then proceeds in a similar way. We'll look at a function of a continuous random variable and how to find its PDF, right? Actually, this is non-trivial. We kind of talked about this, right? We did talk about this in discrete random variable, but we did not give it too much, like, kind of time, because it's kind of easy. This, right, for continuous random variable will have more time, okay? Because it's actually important and it's not easy. So this is where the similarity happens. Continuous random variable being random variable has to have expectation, variance, higher moments, that kind of thing, right? But the formula will be slightly different because now the formula will be using density, right, rather than mass function. Of course, the programs do the same in terms of like the well-known models, but the list of the well-known models, notice, is kind of less. There are only 3 of them. Technically speaking, there are only 2. The normal random variable is always there in the background, but working with it requires numerical tools and things like that. So, right, the uniform and the exponential. It's not because, right, that there are less well-known continuous random variables, right? We mentioned right here the chi-square, the t distribution. There's also the Cauchy is a part of a t distribution. The chi-square, the t, and what else? The gamma, right, and the beta, right, for example, are well-known continuous distributions. The only thing with continuous distribution is actually they are kind of slightly harder to work with, or the density is more involved. So we tend to we'll focus on the sort of the well-known model anyway. But also another reason is that these are not really model. I mean, when we say model, we mean they really try to describe something that we observe. The chi-square, the t, right? They tend to be what was called the sampling distribution, meaning that they are distribution of statistics, right, in the sample. So in that sense, they don't directly come from a model. They come up in statistical, right, context. And so you will study more about them anyway, right, in classes like Math 481. So we limit our discussion to these ones, okay? Notice that one last thing on this list, right, in the discrete random variables that we do not show here is to, let's say, find the distribution of x plus y, x minus y, x times y, the PDF of. This, in fact, becomes a much, much less trivial thing to do in continuous random variable, okay? And in fact, right, it will require the technique of the Jacobian to deal with in some case, okay? Or convolution and whatnot, or conditioning. But so basically, right, I guess the main message is that continuous random variables are actually more sophisticated than discrete random variables. That's kind of unfair. It's not like it's by nature that much harder to deal with. It's just a tool of the density. It's this guy right here, right? That's the cause of all thing, all right? So pay attention to the density and learn how to work with it correctly. All right. So the density, right? So a continuous random variable, right, always has density. So notice right here, I guess the typesetting might look a little bit hard to see, but this is capital X for the random variable. Little x is for the value, right, of a particular value, right? So this x right here is just a membership, right? This little big X is the membership. Little x is the value that random variable take. Okay. So the density of a continuous random variable is just like the density in physics, right, of a piece of wire. The reason why we say the density of a piece of wire and not like a disk or something like that you're more familiar with, let's say a piece of wire of that length, right? The reason is because we are dealing with one-dimensional distribution, right? We're not dealing with two-dimensional or multi-dimensional distribution. So that's why we don't have density in like a ball or a disk, that kind of thing. We could, actually, that's perfectly fine, right? That's joint density. But later, right? For now, it's a one-dimensional density. So like a density of a wire, right? The mass density of a wire. So of course, density cannot be negative, okay? And here, right, the total mass is 1, right? But notice that this integral, when we write minus infinity to infinity, that's just really because we do not have the support of the random variable written out explicitly. It changes from random variable to random variable. But, right, basically, for example, the uniform, right, has support from A to B. Then the integral here is the integral over the support of the random variable. okay, to be precise. But this is not incorrect. The reason is the density actually is extended to be defined to be 0 outside the support. So the integral over the whole real line is not incorrect, right? It's just useless to integrate 0 right outside the support. It doesn't do anything. But right, it basically says total mass is equal to 1, right? So here are the two examples, right, of the density of a random variable. So what is the meaning of the density, right, for example? So yeah, let's take a look at, let's say here, right, or the exponential, right? So what you have, right, is a density graph over a support, right? Notice this is 0 outside the support. So the total mass here is 1, right? The total area is 1. And that actually, right, is of course equal to the total probability, right? The total probability of being inside this interval is equal to 1. Is 1, right? So that's why it's a support, right? But more than that, right? For example, the idea that say you are in between two values right here, let's say some other value, right? Let's say S to T. Then you will have a area under the curve, right? Then the probability that you are, let's say between S and T. Notice, right, equality doesn't matter in the continuous random variable because, right, it's taking on any exact value with probably 0. So you can write equality or not, right? It's the same thing. But anyway, right, it will be, well, not roughly, but actually it's the area, right, under a curve from S to T divided by the total area. So it has that idea of the ratio anyway, right? But the total area is 1, right, by definition. So that's why, right, the area under the curve will become the probability, right? But so basically the density serves as kind of that anchor, right, for telling you how your area under the curve will move, right, as you move along the possible values of x, right? Here, for example, the exponential, there are several curves here because, right, they try to give you different graphs, right, for different values of the parameter of the exponential, right? We'll get there later. But it's the same idea, right? For example, if you want to know the probability, the exponential is between 0 and 1, or, you know, let's say 1 to 2, right? For any of this curve, you will look at the area under the curve. Let's say of this, right? I don't know what this color is, green, magenta, whatever, right? Probably green, right? So anyway, you look at the area under the curve here, right? Over the total area, right? That's going to be the probability. But again, the total area is 1, so it ends up being the area under the curve. And the density, right, gives you that idea of how the probability moves as you move along different region, right, on the support. Okay. Of course, right, notice one thing here that's kind of obvious already, right? That with the uniform, right, doesn't matter where you move, the probability seems to be similar, right? But that, notice, is a very, very wrong statement, a very imprecise statement. Of course, the probability is not the same because the probability depends on, you know, how wide you want to take the base to be, right? What you're saying is the probability density is the same. And of course, right, it has constant density. That's why it's called uniform, right? The probability density is the same everywhere, right? So what you're saying is that as long as you have the same length of interval, S prime to T prime, then the probability falling under that interval will be the same as the probability falling under the same interval st, right? As long as the length are the same, because the density is constant. With a uniform, right, you see that the story is different, right? With the exponential. With the exponential, you see, right, if you are out here, right, the further out you go, the faster, right, the density decays. So for the same length, right, of interval, let's say 4 to 5 compared to 1 to 2, right, the probability that you fall between 4 and 5 will be much smaller than compared to falling under 1 and 2, right? So there's the exponential decay in the density of the exponential distribution, right? So that's the meaning of the density function. It controls, right, the likelihood, right, as you move along different region of the support. Okay, any question about this? But we should note right away that the density is not a probability. Okay, this is like mistake 101 for even someone who comes out of this class. They would come up and say, yeah, let this density be the probability, blah, 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 right? That statement in of itself is a lot of nonsense. Okay, density is not a probability. So that's why we need to distinguish, right? For the discrete distribution, mass function, PMF, is a probability. All right, probability x equals to x, of course, is a probability. That's why when you work with discrete random variable, you don't even think too much about it because you, by default, work with probability. With continuous random variable, you by default work with density, which is not a probability, right? So therefore, rules of probability does not apply to it. Okay. For example, it can be bigger than 1. Of course, right, it's still non-negative, but that's its own rule rather than the rule probability, right? Because the density has to be non-negative anyway, right? But for example, right, look at here, right? The density of a uniform is 1 over b minus a. So clearly, for example, b minus a is 0.5, then the height here is 2, right? The density can be bigger than 1, right? That's fine. And for that reason, right, that just for this very simple reason, right, is not a probability. However, right, the thing that kind of will come back and kind of haunt you if you're not quite clear about all these things is that even though it's not a probability, it still represents something called a likelihood. So that's a different word, okay, to represent, okay, right, well, chance, whatever. But it's used as a different word because, again, we don't want to mess around with the word probability because the rules of probability, the axiom of probability do not apply to density, okay? There's no such thing as the density of an event as, I don't know, right? Sorry, F. Right, I don't even know if anyone can entertain this kind of thought. But again, right, even writing this down is nonsensical. Again, right, trust me on this, it's actually not that strange, for example, to see something like this. So probably they won't plug in an event, but they will plug in values. And again, right, something like that is complete nonsense. Okay. So, but it represents likelihood because, right, again, you see here, right, what we're saying is that as you travel along the support of the uniform, you have the same likelihood of falling into region of the same length, right? While the likelihood of the exponential, right, decreases as you travel along. And this should be mentioned because, right, if you move on from this class and take a class in parametric statistics like 481, then there is a very, very powerful method, right, called MLE, right, the method of maximum likelihood, right? MLE is like maximum likelihood estimator, right? That relies on the density as being the likelihood, right? So in which case it seems like it's being treated like a probability, but it's a different concept, okay? So it's not a probability. So that's also why, right? To work with the density, right? Or if you want to apply rules of probability, then you need to integrate the density to work with probability, right? And that's why things like the CDF, cumulative distribution function, becomes a necessity in a continuous random variable, right? In discrete random variable, you don't have to use it because you have probability to work with to begin with. In continuous random variable, you cannot work with the density in terms of probability, right? Using rules of probability. So if you want to top a probability, you have to integrate the density. So the CDF, all right, is the like tool that you have to go through, all right, to work with in continuous random variable. Any question about this? All right. So yeah, right here, the CDF has to be used, right? So you differentiate CDF, you get PDF. You integrate PDF, you get CF at that point, right? Notice this integration is all the way from the left, right? We do not know, again, the support of the random variable, so we have to put minus infinity there. If you know a definite place it will start, like a uniform or an exponential, then you can plug in, right, a more appropriate value. Okay. Any question? All right. So let's start working with density right away. Okay. So let's take a look at this one. How do we find the value of C?
So the integral of fx from -1 to 1 would be 1, so you could get C from there.
Correct, right? -1 minus x squared dx times C equals to 1. By the way, right, integration techniques is required, right, in this part. So, for example, right, and again, right, no calculator help, of course. What's the answer here? What's the fast way to integrate that? First one integrate to 2, right? The second one is twice, like that. So that will give you x cubed over 3, right? So 1/3. So 2 minus 2/3 is 4/3, right? Correct? What about B? So B asks you to write down this CDF, right? Notice that you have to write this down correctly. So how do you write a CDF here? There will be 3 parts to a CDF. It will be 0 if you are below -1. Why? Because, right, you have to list it out for all values, right? And it'll be 1 if you're above 1. Right? In between, what value is it? Or what function is it? So technically speaking, I should use this language. Less than, yeah, that doesn't matter. Right? Any question? Well, make sure, right? For example, at -1, is it 0? At 1, is it 1? At 1, this doesn't look like 1, right? At 1, actually, this is more than 1. So my answer here is wrong. What was wrong here? 2 minus 2 x cubed over 3, that's correct. 2 minus 2/3 is definitely 4/3, right? So 1 3/4, everything seems fine. So I think, what did I make? Where did I make a mistake? This is correct, this is correct, this is wrong. So f of x is, oh, yeah, where's the mistake? So this is actually completely wrong, right? Wrong, for example, right? Because when I plug in 1, right, this value is bigger than 1. When I plug in -1, actually, right, this value is also below 0. The reason, right, is actually this is not just a simple antiderivative, right? So it should be, it's a definite integral, actually, right? It's going to be the integral from -1 to whatever value it is, right, of the, let's say, do you understand? So it's not a simple antiderivative. It's a definite integral, right? So of course you still get something like x here, right? And cube over 3. But you have to kind of subtract the lower value. So it's going to be 3/4 x minus x cubed 3, and then subtract, right? When you plug in, right, -1 in here, 1 second, I'm still getting something wrong. What is the error here? When I plug in -1, that's still 0. So unless my C calculation is wrong, right? But it's not. What's going on here? I'm getting something not quite right. wait, hold on. Everything's correct here, right? But if I subtract, yeah, sorry. If I subtract, right, I should subtract the value when I anti-differentiate and plug in -1. Sorry, I just lost my thought there, right? So if I plug in -1 here, right, that's -1, and that's going to be another -1, right? So that's -1 plus 1/3, right? So 3/4 times -1 plus 1/3, right? So that would be that's -2/3, right? And then times 3/4, that would be -3/4 times -3/4 times -2/3. So that's going to be plus 1/2. Yeah, okay. So that's actually the missing piece here, right? So that's the answer, right? So the point is, a CDF, right, is a definite, right, integral. All right. If you just take the simple antiderivative, then your answer will be wrong. Like I said, right? Because when you plug in, for example, 1 without this piece, right, you get only 1/2 and you won't get 1. And you plug in -1, you won't get 0, you get -1/2. You understand? Any question here? All right. So let's take a look at this one. Oh, sorry. So is this a density function? How do we know?
Fine if there's a like a C that exists to so that the integral of f is 1.
There's always such a C, right? The
Oh.
reason, of course, is when you integrate from 0 to 5/2, right? I guess there's only one exception, of course, when somehow this integral is 0. So yeah, there's that. But if the integral is not 0, right, or positive, of course, right, then there's always such a C, right? So that C, by the way, right, is called the undetermined, call it integrating constant or integrating coefficient. And a lot of densities are given like this one, right? Or this one. The reason is, right, what happens is people just want to give you a graph. Let's say the other one, right, is like a graph like this, right? 1 minus x squared from -1 to 1, right? And they say, I want to use this as a density. Again, right, remember, the broad idea of a density is that it's just a ratio of area. You want to take, let's say, the area over here, right, over the total area. then you will get the probability. So the C, right, just scales everything down to 1. So the C, right, yeah, another name for it would be the normalizing constant. But it's not super important, and a lot of time you can find it. Right, 99.9. That's, in fact, right, even something like this. Let's just take another case. Could I use something like this as a density? Let's say I have a graph like that. Can I use that as a density?
No. Because it's all negative. So is it like the CDF must be non-decreasing?
True. So when I say, right, when I use this as a density, I don't mean exactly using it as a density, but I use the shape or the behavior, right? The answer actually is I can. I just have to multiply everything with minus something. I just have to flip it with a negative C. Right? Then I can use it. Do you understand? So when I say, of course, I mean, my question is not super precise, but when I say, can I use it as a density, or right, case in point, right? For example, instead of having x squared minus 1 here, I have x 1 minus x squared, have x squared minus 1, right? Then is that still a density? Yes, right? With what value of c? C goes to minus 3/4. You understand? So even in that case, I can do that. Okay. So as long as, of course, right, blatantly doing this is wrong, because then there's no choice here, right? You have set everything. But when you give a C and you say you give a room to choose C, then you can do a lot. So the question is, right, is there a case when you cannot do so? The answer is when it's half and half. In other words, it's something like this. Some parts positive and some parts negative. You cannot use such a function as a density, right? Even with a C in front. Because a C, right, can only turn it one way or another, right? You cannot turn both parts to be positive. You understand? So when you have a function, right, the only time when it cannot be a density is when it's a mix of positive and negative values. Right? If it's entirely negative, you can still do it. Entirely positive, of course. All right. So from that point of view, right, is this a density? Can this be a density? What is the graph of this from 0 to 5 halves?
You would have a 0 at x's uh square root of 2, so I don't think it works.
Correct, right? Square root of 2 exactly is below 5 halves, right? So how does it work? 2x minus x cubed, right? Does it start to be positive or negative? So 2x minus x cubed, right? It should be positive up to square root of 2, right? And then square root of 2 is a single root. And so it will go like that. Agree? So yeah, right. Because of that, the answer is no.
Professor,
Any-
can you say again like why it could be like all negative?
Again, just turn this question around. F of x equals c x squared minus 1, minus 1 less than x less than 1. 0 otherwise. Can f be a density?
Oh, so in this case it's just like C changing.
Say again.
And so like in this case it's just C flipping the signs.
Yeah, that's what I'm saying. Right?
Ah, okay. Okay.
You can, as long as the function does not change sign within the support, you can choose a c that would flip it around, right?
Okay.
So that integrating constant can do both jobs for you. Most of the time, people won't do something weird like this to begin with anyway, because they understand that c will flip, so they just write it down as positive to begin with. But conceptually, there's nothing wrong with it being entirely negative, right? C can take care of that. Only when the function is half and half, then there's no c that can fix it for you. Okay.
Hmm.
All right. Any other question? All right. So good place to stop here, right? Let's continue with this on Friday. Okay.